In this video, we are still going to continue with the miscellaneous related questions on the mole concept and stoichiometry. The mole concept and stoichiometry. So we'll be starting with question number 3. But before we continue, I really want to appreciate those of you who have subscribed to my channel. And then for those of you who haven't subscribed to the channel, please support us by liking the video, by making comments, and subscribing to our channel. Welcome back. Thank you for taking your time to subscribe. Let's get started. Question number 3. Calculate the 3A. Calculate the volume in dm cube occupied by 26.4 grams of carbon dioxide at room temperature and pressure. The AR, that's the relative atomic mass value for carbon is 12, and for oxygen is 16. Then B part of it, a flask of volume 120, excuse me, 120 cm cube is filled with helium gas at room temperature and pressure. Calculate the mass of helium present in the flask. The AR value of helium equals to 4. That is 4 grams per mole. Okay. This is what we call, we are not going to be dealing with the molar gas volume. The molar gas volume. When you hear in an examination question, when you hear a gas occupying a particular volume at room temperature and pressure, we are not talking of molar gas volume. The molar gas volume. And you should know that the molar gas volume is the volume occupied by 1 mole of any gas at room temperature and pressure. Once more, the molar gas volume is the volume occupied by 1 mole of any gas at room temperature and pressure. And 1 mole of gas occupies 24.0 dm cube at room temperature and pressure. So 1 mole of any gas will occupy 24.0 dm cube excuse me, dm cube at room temperature and pressure, sorry. So now, going back to our question number 3A, calculate the volume in dm cube. Now, from the data that we have got, we have to use the relation moles. We have to use the relation moles, will be moles which will be equal to mass all over the molar mass. The molar mass, you can write it as MO. So now, you must use that, we will use that relation. And if we use this relation, we are told the volume, calculate the volume in dm cube occupied by 26.4 grams of carbon dioxide Now, we need to look for the molar mass or the MR of carbon dioxide. Carbon dioxide is CO2, and we are given carbon is 12 and oxygen is 16, which will be it will be 12 plus 16. 16 times 2. 12 plus 16 times 2, and that will be a total of 44. Will be 44 gram per mole. That will be 44 gram per mole. So now, we go back to our calculation. We will have 26.4 gram divided by 26.4 gram divided by 44 gram per mole. And if we do that, do our calculation very well, this is what we are going to have. The gram will cancel out the gram, and we'll be left with that. And our answer will be, if we divide this by this, we are going to have 0.6 moles of carbon dioxide. That is not our answer. That is not our answer. We have 0.6 mole of carbon dioxide, but we are told occupies at room temperature and pressure. And I said at room temperature and pressure, we are now talking of molar gas volume. And every molar gas volume, 1 mole of every molar gas volume will occupy 24.0 dm cube. So this is the volume occupied by 1 mole of any gas at room temperature. So at room temperature and pressure, 1 mole of a gas will occupy 24.0 dm cube. So now, we now go now, our simple proportion will be, if, you are still on A, if 1 mole of a gas, or a 1 mole of carbon dioxide, a 1 mole of carbon dioxide occupies 24.0 dm cube at room temperature and pressure. Therefore 0.6 moles of carbon dioxide will occupy what? Will occupy a certain volume we don't know. Will occupy x mole per will occupy x dm cube. So now our x value would now be 0.6 mole times 24.0 dm cube divided by 1 mole. So now if we cancel out this, you will see that the mole here will cancel the mole here, and the 0.6 times 24 will give us the volume of carbon dioxide, and that volume will be 14.4 dm cube of carbon dioxide at room temperature and pressure. So that is how you can get this type of calculation. So remember, in an exam, when you are asked to calculate a volume of gas and you are mentioned room temperature and pressure, please use the molar gas volume. Use the molar gas volume. And in this case, you need to convert everything to mole and then make your proportion. Because at room temperature and pressure, 1 mole of a gas will occupy 24 dm cube. That is why using this information here, we have been given the mass, and we have given the relative atomic masses. So the only thing is to calculate the number of moles of carbon dioxide. After getting the number of moles of carbon dioxide, we went further and relate it. If 1 mole of carbon dioxide occupies 24 dm cube at room temperature and pressure, therefore the 6 moles of carbon dioxide that we have calculated will occupy X, and our X now is 14.4 dm cube of carbon dioxide at room temperature and pressure. It takes us to question number 2, which is question number 4. It has to go to the mass spectrometer again and isotopic masses and relative abundances. Now, question number 4. No. We have not done question number the B part of it. Sorry, we have just done this is the A part. This is the A part of it. This is the A part that we started here. This is the A part. Then the B part of it. This is the B part that we have to start here. The B part of it says, the B part, a flask of volume 120 cm cube is filled with helium. A helium gas at room temperature and pressure. We are now dealing with gaseous molar gas volume. Now calculate the mass of helium. In this case, this is a question you have only been given the volume, and you have been given the condition, that is room temperature and pressure. What you need to do again, use the molar gas volume. So how can we use this volume to have our molar gas volume? The first thing you do here is, since the molar gas volume are calculated in dm cube, we have to convert this to dm cube. We have to convert 120 cm cube to dm cube, and then from there we can work it out. 120 cm cube. But the B part of it, 120 for helium, 120 cm cube is equal to 0.12 dm cube. It's very simple. When given the volume, try to bring it to the units that you can use to easily calculate in molar gas volume. And once room temperature and pressure is mentioned, go to molar gas volume. So now we convert our cm cube to, or our cubic centimeters to a cubic decimeter, a dm cube. Now we can now use our simple proportion. We can say if 1 mole is helium gas, the atom of helium gas, 120 is filled with helium gas. We can now simple proportion. Very simple. If 1 mole of helium gas, let me just say helium gas occupies 24.0 dm cube at room temperature and pressure. Then X moles of the helium gas will occupy say, it will occupy what? It will occupy, what is the volume we calculated? The volume here is 0.112, will occupy 0.112 dm cube at RTP at room temperature and pressure. So it's a simple proportion. After converting your cm cube to dm cube, now let's use our molar gas volume. that if 1 mole of helium occupies 24 dm cube at room temperature and pressure, then what mole, how many number of moles of the helium gas will occupy 0.112 0.12 dm cube? If we use this simple proportion, we will come to this. Our value of x will be, we will have 1 mole, times 1 mole times what? Time cross multiply 0.112 dm cube. 1 mole times 0.112 dm cube divided by what? Divided by 24.0 dm cube. If we do that, we will cancel out this, and this. Now we are now looking for the number of moles, and the number of moles of helium here will be, 0.005 moles of helium. That was the number of moles of helium. Now, after getting the moles of helium, what is the mass? The question was calculate the mass of helium present in the flask using the number of moles and using the expression of moles. We have moles equals to the mass all over the molar mass, mR molar mass. So if we want to have the mass, we will cross multiply. So the mass will be moles times molar mass. So now let's get back again. So our mass of helium, the mass of helium will be moles times the AR. That is the relative atomic mass, which is AR, and that will be equal to the number of moles here is 0.005 5 moles times the relative atomic mass of helium. We were given it to be 4 grams. It is usually 4 grams per mole. 4 grams per mole. 4.0 gram per mole. 4.0 gram per mole. Yeah, 4.0 gram per mole. So in that case, we will cancel the mole. We'll cancel per mole. We will not be left with grams. And what will be the mass now? The mass now will be 0.005 times 4, which will be 0.02 gram of helium. That will be the mass of helium. So as I said, when you are given this, you need just to convert it into the dm cube, then use the simple proportion that if 1 mole of helium gas occupies 24.0 dm cube at room temperature and pressure, then x moles of helium will occupy 0.112 dm cube at room temperature and pressure. And you've solved for the value of x. After solving the value of x, you have the moles of helium. Then you can now say, so you have the moles of helium. We have a relation which is mole time, mole equals to mass all over the relative atomic mass, or the relative or the molar mass. Now you can look for the mass by multiplying the number of moles by the relative atomic mass. So the mass of helium will be the number of moles times the relative atomic mass. That is AR, relative atomic mass times the number of moles. and the number of moles was 0.05 moles times the times 4 gram per mole, which is the relative atomic mass for helium, and we will have our 0.02 gram of helium. Question number 4. Question number 4 has to do with relative atomic mass. In relative atomic mass, I told you that relative atomic mass of an element, we did it in most of our papers. So I can still say the relative atomic mass is the average mass. This is the average mass. This is the average mass of naturally occurring atoms of an element on a scale where the carbon-12 atom has a mass of exactly 12 units. Once more, the relative atomic mass is the average mass of naturally occurring atoms of an element on a scale where the carbon-12 atom has a mass of exactly 12 units. 2. The second part of it, a sample of excuse me a sample of boron a sample of boron was found to have the following percentage composition by mass. Boron is an element of the periodic table. So now a sample of boron was found to have the following percentage composition by mass. We have boron 10. There are two isotopes of it. There is boron 10 and boron 11. So boron 10 had a percentage of 18.7%, and the boron 11 had a percentage of 81.3%. Calculate a value of the relative atomic mass of boron. Remember, we said this is the average mass. The relative atomic mass is the average mass of naturally occurring atoms of an element on a scale where the carbon-12 atom has a mass of exactly 12 units. So we are now going to have the average. See how the average of the relative atomic mass is going to be calculated. Calculate the value of the relative atomic mass of boron. Give your answer to 3 significant figures. Now, you can equally define the relative atomic mass. You can equally define it as this is the ratio of the weighted average. This is, let me give you this definition. This is another definition. If you don't define as the other one I gave you, you can use this one. You can use this one. This is the most updated one. You can say that relative atomic mass. You can say this is the ratio. You can say this is the ratio of the weighted average mass. The weighted average mass of atoms in a given sample. In a given sample of an element. In a given sample of an element to the unified atomic atomic mass units. So this is the most updated definition for the relative atomic mass. Now it is being defined. The two are acceptable, but this is an updated version of it. That this is the ratio of the weighted average, the weighted average mass of atoms in a given sample of an element to the unified atomic mass unit. So you can choose to use the other one or you can choose this one, but I will prefer that you use the updated, which is this one. So let's go back to our calculation. Okay, a sample of boron was found to have these percentages. Calculate the relative atomic mass of boron, giving you an answer to 3 significant figures. There is a formula for the calculation of relative atomic mass. And the formula I can give you, let me give you this formula here for the calculation of the relative atomic mass. The formula is, let me say, relative atomic mass. Relative atomic mass. Let me say relative atomic mass is equals to the percentage abundance. Percentage abundance. Oh, sorry, please. Percentage abundance. Percentage abundance times the atomic mass unit. Atomic mass unit for each isotope. For each isotope divided by what? The total percentage of the total percentage abundances. Total percentage abundances. So in this case, this is what I really mean by this. Percentage abundance times the atomic mass unit for each isotope. If there are 5 isotopes there, you need to put all of them and then divide by the total percentage abundances. So in this case, what was given for boron is 18.7. Boron here was 18.7. That is for boron 10. Then 81.3 for boron 11. And the total percentage is 100. That is 87.81. So applying this here, we will say the relative atomic mass of boron will be what? Boron 10 had 18.7. That is the relative abundance times the atomic mass unit. Atomic mass unit is the atomic mass, that is the boron 10, which is 10, yeah, plus, then boron 11 had, the percentage was 81.3. Boron 11 means it had a mass of 11. That is atomic mass unit of 11. So that, then if we add 18.7 plus 81.3, we'll have a total percentage abundance of 100. And if we do this, the relative atomic mass, if we calculate this, the relative atomic mass of this will be 10.8 atomic mass units. 8.10 for helium. I mean, for boron, sorry, for boron. That is the relative atomic mass for boron. The relative atomic mass, atomic unit, that is for boron. For boron. So now, that is the mass that you have been asked, and into the give your answer to three significant figures. So it's 10.8. It takes us to the third section of the question, that's to the B part of the question. The B part of this question is telling us about boron 3, boron 3, boron 3, that is B. Boron 3 plus has boron 3 plus can be formed by bombarding gaseous boron with high energy electrons in a mass spectrometer. Once more, boron ion, which is B3 plus, can be formed by bombarding gaseous boron with high energy electrons in a mass spectrometer. Deduce the number of electrons in one boron 3 plus ion. The cation of boron, that is the B part of it. The B part of it, that is boron 3 plus. This is a cation, and the boron has boron has an atomic mass of what? From what we were told, it has atomic mass of 10.8. That's the atomic mass. But look at this here. What is the mass number? The proton number. The proton number of boron is 5. Remember, the number of protons are equal to the number of electrons. The number of proton are equal to the number of electrons. And the proton number is equal to the atomic number. Now we have the atomic number of boron to be 5. And the boron 3 ion has been formed. They now tell us find the number of electrons in boron 3 plus. Having an atomic number of 5, boron has an atomic number of 5. Boron has atomic number equals to 5, which is equal to 5 electrons. It has an atomic number of 5. It has a proton number of 5. And the atomic number, which is equal to 5, is equal to 5 electrons. But 3 electrons have been removed based on the charge here. But 3 electrons have been removed. But 3 electrons have been removed. 3 electrons have been removed, or we can say lost. Can say have been removed, or they have been lost. Now, number of electrons left. Number of electrons. Number of electrons left in B3 plus will be equal to what? 2 electrons. So if you are asked to look for this, boron has an atomic number which is 5. An atomic number is equal to the number of electrons, or which is equal to the proton number, the number of electrons. But 3 electrons have been lost because of a charge of plus 3. Now we are only 2 electrons that are left there. So that is a very simple question for you. Now they go again to say, use the relative atomic mass AR value below to calculate the relative molecular mass of ion 3 borate. That's good. At times, such questions are being asked. So, that is C1. C1 will be C1 to have the relative molecular mass, the relative molecular mass for ion 3. That is boron O2 O, that's 3. The relative molecular mass for this would be what? The relative molecular mass for this would be, if we calculate this here, we are going to use it as iron is 55, given that is 55.5, now 55.8. 55.8, that is iron is only 1, plus boron is 10.8, 10.8 times 3 outside here, plus oxygen is 16. 16 times 2. 16 times 2, but there are two oxygen atoms here. Then times 3 outside here. If we sum up all this, that is iron, which is 55.8, plus boron, which is 10.8 times 3, because of the 3 outside here. Then oxygen here is, oxygen is 16 times 2, then times the 3 outside. We have this, and if we sum all this, we will have the iron 3 boron to be, our value there will definitely be 184.2. That will be the value. 184.2. Then the last section of the equation is asking us the accurate relative atomic mass. The accurate relative atomic mass of iron is 55.8. Explain why the accurate relative atomic mass is not a whole number. That is, why is it that this is having this is having a decimal there? Is not a whole number. Why are relative atomic masses having decimals, not a whole number? That's the same thing we calculated here. It's the same thing we calculated here for boron. You saw that we calculated boron and it gave us 10.8. It was not a whole number. Because of what? These are isotopes. These are isotopes. The different isotopic masses are the one contributing to it. When there are isotopes in an element, when an element contains isotopes, the relative atomic mass will not be a whole number. The relative atomic mass will not be a whole number because we are talking of an average. We are saying that is the average mass of naturally occurring atoms that are there. So the average of these cannot be a whole number. So our simple reason we can give for this, answer here, that the accurate relative atomic mass of iron is 55.8. Explain why the accurate relative atomic mass is not a whole number. It is not a whole number because that is C2. 2. It is not a whole number because iron has several isotopes. So the relative atomic mass of any element is, once it is in fraction, once it is in decimals, not a whole number, know that it is as a result of the isotopes there. Because to calculate the relative atomic mass, we say it is the average mass of naturally occurring atoms of an element. So it's the average mass of it. So when we take an average of all these, it won't give us a whole number, but it will give us the number will end in decimals. So the simplest reason you can give for this answer is because Iron has several isotopes. It takes us to question number 5, the last section of it. Question number 5, it still has to do with the mass spectrometer, isotopes, and how you can calculate the relative atomic masses and everything like that. So let's get to the point. The mass spectrum of zirconium, is shown below. From here you have the chart, you have the curve there, the relative abundance in percentage, and the mass and the charge. The mass and the charge is on the x-axis. So we have from 90, 91, 92, 93, 94, 95, and to 96. Use the information from this mass spectrum to calculate the relative atomic mass of zirconium. Use the information here to calculate the relative atomic mass of zirconium. I told you that to calculate the relative atomic mass of any isotope, or of any element, what you need to do is percentage abundance times the atomic mass unit. Percentage abundance times the atomic mass unit. And in this case, the percentage abundance here is 51. Atomic mass unit is 90, plus percentage abundance here is 11.2. The mass unit is 91. Percentage abundance here is 17.1. Mass unit is 92. In that order, percentage abundance here is 17.4. 17.4. And the mass unit is 94. Atomic mass unit is 94. Percentage abundance here, there's nothing for 95. For here is 96. The percentage abundance is 2.8. And the atomic mass unit is 96. When you do all this and add them, you now divide by the total of the percentages. And the total of the percentages is 51.5, 11.2, 17.1, 17.4, and 2.8. When you divide it, you will have your relative atomic mass. Let's get started. So in this situation, the relative atomic mass, or can say A will be equals to what? Will be equals to, that is 1. But the relative A will be equals to 51, from the information I say 51.5, times 90 plus 11.2 times 91 plus 17.1 times 92 plus 17.1 times 92 plus 17.4 times 94 plus 2.8 times 96. Here you see that this is 90, this is 91, this is 92, this is 93. 93 has nothing, 94 has something, 95 has nothing, 96 has something. So we have 1, 2, 3, 4. We have 4 of them, which we say it is 1, 2, 3, which we say it is 51.5 times 90. Yeah, from 90, yeah. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Divided by, I said, the relative percentage abundance times the the atomic mass unit. These are the atomic mass unit on the x-axis. So we are multiplying the percentage abundance times the relative atomic or the atomic mass units. So the percentages are 51.9, 51.5, 11.2, 17.1, 17.4, and 2.8. When we add this all, our total will be 100. Our total will be 100. And if we divide this, this will be equals to 9,131.8. 9131.8 divided by 100. And what will be the answer? It will be 91.3 atomic mass units. That will be for zirconium. That is the mass for zirconium. For zirconium. That's the mass for zirconium. Then the last answer is, the last section is high resolution mass. High resolution mass spectra was high resolution mass spectra shows accurate relative isotopic masses. Again, high resolution mass spectra show accurate relative isotopic masses. What do you understand by the term relative isotopic mass? Relative isotopic mass. Relative isotopic mass. The relative isotopic mass, that is 2. Relative isotopic mass. We can define the relative isotopic mass as the mass of a particular atom. The mass of a particular atom of an isotope compared to the value of the unified atomic mass unit. So we can define the relative isotopic mass as the mass of a particular atom of an isotope compared to the value of the unified atomic mass unit. So that is all we have. I have for you today. A recap of what we have just done. I said we are continuing with some miscellaneous related questions on physical chemistry and stoichiometry. And we were given a volume occupied by a certain mass of carbon dioxide. And now we are asked to calculate the volume in dm cube. You were given the mass to calculate the volume in dm cube. Remember, when you enter into an examination room and you are asked to calculate a particular volume and they give the condition to be room temperature and pressure, please use the molar gas volume. This is the volume occupied by 1 mole of a gas at room temperature. And I told you 1 mole of a gas will occupy 24.0 dm cube at room temperature. So now that carbon dioxide has been given, only the mass was given. Do everything, do the relation, use any formula you can to have the number of moles of carbon dioxide. And we did that. We used moles mass divided by molar mass, and we did that. We had 0.6 moles of carbon dioxide. Then how can we now convert this to molar volume? After having the 0.4 moles, the 0.6 moles of carbon dioxide, remember 1 mole of a gas occupies what? 24 dm cube at room temperature. So the only simple ratio, simple proportion we can use in this situation, we can say if 1 mole of carbon dioxide occupies 24.0 dm cube at room temperature, then the mole that we have calculated, the calculated mole, which is 0.6 mole of carbon dioxide, will occupy what? When you have that, you have the number of, you have the volume. And that volume will what? That volume is in dm cube. We calculated that it was 14.4 dm cube. We went further again to calculate that we should calculate the mass of helium, given only the volume. We don't have any relation that is going to use only the volume. So what we need to do is to convert the volume to dm cube, then use the molar gas volume. Why must we use the molar gas volume? Because we have been stated 120 cm3 is filled with helium gas at room temperature. The condition room temperature and pressure gives us that room to use the molar gas volume. So after converting 120 to dm cube, now we can use again our simple proportion. We can use our simple proportion by saying that by saying that 120 is equals to 0.112 dm cube. And we can say if 1 mole of helium gas occupies 24 dm cube, then how many moles of the helium gas will occupy this 0.12 dm cube? We calculated it and it gave us 0.005 moles of helium. That is the mole of helium. But we are told calculate the mass. Remember in our relation we said, look at the relation up here. We said moles equals to mass divided by molar mass. Molar mass or relative atomic mass, in case you are dealing only with an element. So in that case, the mass will be what? The mass will be the number of moles times the relative atomic mass. And we're given the relative atomic mass of helium to be what? To be 4. So now we have the number of moles. So the mass of helium will be the moles times the relative atomic mass AR, which is given there. And it will be 0.005 times 4 grams per mole. The units will cancel out, and the mass of helium that will be left will be 0.02 gram. It took us to question number 4, still on relative atomic masses. I gave you the definition of relative atomic mass. I gave you the relative atomic mass, and I came again and said the recent or the updated definition of the relative atomic mass is this is the ratio of the weighted average mass of atoms in a given sample of an element to the unified atomic mass unit. Finish. Then it drove us to the second part of it. A sample of boron was found to have the following percentage. A following percentage composition by mass. They gave us boron 10 to have 18.7 and boron 11. I call it boron 11 because it has atomic mass of it have a nuclear number, or what we call the atomic mass of 10. I call it boron 11 because it has a nuclear number of 11, or what we call atomic mass of 11. So boron 11 had 10 had 18.7, boron 11 had 81.3. And I gave the formula to calculate the relative atomic mass. I said to calculate the relative atomic mass of any element given the different isotopes, what you do is the percentage abundance that has been given times the atomic mass unit for each of the isotope. Then divide it by what? Divide it by total percentage of abundances. And boron 11 was 10 was 18.7. We multiplied the percentage abundance, which was 18.7 times 10 plus 81.3 times the boron times 11, which is the atomic mass unit, divided by the total of the percentage. The total of the percentage was what? 18.7 plus 81.3. It gives us a total of 100. And when we divided it, we have 10.8. And the unit is atomic mass unit. That is the relative atomic mass for boron. We went further again, and they asked us, boron has this cation. The cation there is B3 plus. How many electrons are there? Remember that the cations, when the charge, the positive charge in any cation signifies the number of electrons that have been lost. If one electron is lost, it means that you have one positive charge. If there are two, you have two positive charges. If there are three, you have three positive charges. In this case, boron has lost 3 electrons. And the boron has an atomic number of what? An atomic number or a proton number of 5. Atomic number or proton number is equal to the number of electrons. So if there are 5, then there are 5 electrons. And from the 5 electrons, if 3 electrons have been lost or have been removed, now how many electrons are left? We now say number of electrons left in B3 plus. In boron cation is there are 2 electrons that are there. They went further that we should calculate the relative atomic mass, the relative molecular mass for iron 3 borate, and we use the information that was given to calculate it. And finally, the last thing that we're told was that the accurate relative atomic mass of iron is 55.8. Explain why the accurate relative atomic mass is not a whole number. I told you that to calculate the relative atomic mass of any element or the atom, what happened is that it is the average mass of the atoms that are there, the average masses of it. So when we take average of all the isotopes, in that case, there are many isotopes. When we take an average of it, that is, we take the percentage abundance times the atomic mass unit for one isotope plus the other one, and we add all them and divide by the total percentage abundance. You will see that it can't be a whole number because of the presence, because there are many isotopes involved. So our simple explanation here why iron is having but a decimal, not a whole number, is that iron has several isotopes. Then it took us again to the last section of it, which was the mass spectrum of zirconium. Again, we were given this is an analysis of a mass spectrometer where the analyzer has given us the abundances and they have given us the different masses of the isotopes that are involved. These are the different isotopes. We have their relative abundances. We have their relative atomic mass units. Now, we have been asked, use this information to calculate the relative atomic mass of zirconium. Again, using the same formula I told you, relative abundance, percentage abundance times the atomic mass unit, relative percentage abundance times the atomic mass unit for each of the isotope. So we took for the first one was the percentage abundance was 51.5. Then the atomic mass unit of it was what? Was 90. So we added to the other one, which is 11.2 times 91. Then to the other one, which is 17.1 times 92. Then the other one, which is this 17.4 times 94. Then the other one, which is 2.8 times 96. And when we add all the percentages, the percentage abundances, 51.5, 11.2, 17.1, 17.4, 2.8, a total of it will be 100. And then when we divide the sum of these by 100, when we divide this by 100, what we are going to have will be 91.3 atomic mass unit. Again, you have seen that The relative atomic mass for zirconium is not a whole number. It is a fraction because of what? The involvement of several isotopes in it. So now, they now tell us what is relative isotopic mass. What do you understand by relative isotopic mass? I said the new version or the updated definition of relative isotopic mass is this is the mass of a particular atom of this is the mass of a particular atom of an isotope compared to the value of the unified atomic mass unit. And that was how we ended our discussion today. Thank you very much for listening. I'm wishing you the best in your exams. But before you go, please like the video, share the video, and endeavor to subscribe to our channel. Once more, thank you for those of you who have already subscribed. I thank you once more for a job well done. Thank you. Bye-bye.